the horizontal asymptote? Negative 2, thank you. It's y equals k. Yep. Okay, let's make our xy table then. How do we choose the x's? I do negative 2 plus h, negative 1 plus h, this is h, 1 plus h, and then 2 plus h. Okay with that? How do I find the y's? I can either plug the x's back into the function, right? You can always do that. Or you could use the little formulas that I gave you. So the first, if we use the formulas, that's a times b to the negative 2 plus k. That's going to be a pretty gross looking decimal. So let's just use the calculator to do this. We'll type them in. It'll probably just be a little bit easier. So that's negative 2.2 repeating. And the next one, I want to change that to a 1. It's negative 2.6 repeating. And then that one I can do in my head. That's negative 4. I guess I could probably do the rest of these in my head, to be honest with you. Negative 8. And then the last one is negative 20. Okay. So there's my XY table. Let's kind of draw our XY axis and plot our stuffs here. 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. First thing I like to do is draw in my horizontal asymptote. So there's my horizontal line that goes through negative 2. And then we'll plot some points. So I got 0, negative 2.2, 1, negative 2.6, 2, negative 4, 3, negative 8, and 4, negative 20. So there's my graph. Okay on that? So far, so good? The last thing to do is the domain and range. Well, the domain is easy. It's always negative infinity to positive infinity for all of the exponential functions. The range, though, depends on two things. We have to look at the value for a and the value for k. Since the a value is negative, we're going to start with negative infinity. And because the k value is negative 2, we end with negative 2. So there's our solution for 3. Matthias? So negative 2 is k?
No, I mean the k. I took the k.
Oh, because the b value is greater than 1.
Oh, I just drew it the wrong way.
Right? So if we go back and I look at the b value, that's all. So we're just looking at the b values. Lexi, you happy?
Yeah.
Oh, good. Does anyone else want to talk about any of these, Matthias? Well, we have to do the whole thing because I don't have like the graph ready, but we can do number 2. You want to? So that was y equals -1 times 0.5 to the, what was the rest of it? Wonderful, thank you. So first things first, we'll write down our values for a, b, h, and k. Everybody agree there? Notice that the b value is less than 1, so that's decay. For our horizontal asymptote, that's y equals k. And then we'll make our xy table. So I'm going to have -2 plus h, and then -1 plus h, +1 plus h, and then +2 plus h. And then we can find our y coordinates by just typing these into our calculator. So that's the way I'm going to do it. You could also use the formulas that I gave you in class. That's fine also. So there's 0. 2. 3. I should probably write some of these down. 3.5, and then 3.75 probably. Yep. Okay. So there's my xy axis. First thing I like to do is draw in my horizontal asymptote. Then let's plot our points. So I have -5, 0, -4, 2, -3, 3, -2, 3.5, and then -1, 3.75. So if I draw my function, it should look like this. The domain is always -infinity to +infinity. And the range, again, depends on two things. It depends on the value for a and the value for k. Since a is negative, I know I start -infinity and I end with k. So that's that. Matthias, are you happy there?
Yeah.
Ty, what's up?
So the asymptote is going like where on the graph the k value?
Yeah, it's a horizontal line that goes through that value of k. Yeah. Yeah, no problem. Oh, I meant this +4, excuse me. Right? Yeah, makes more sense there, huh? All right. Do we feel okay about these questions here? So they shouldn't be too bad, right? Relatively easy. All we have to do is kind of follow the procedure we outlined in the notes the other day. Okay. So today we're going to talk about some applications of exponential functions. So the first model that we're going to look at is called the exponential growth or decay model. And that equation is y equals a times 1 plus r to the t, where y is going to be the final amount, a is the beginning amount, r is the rate of change written as a decimal, and t is time. The second equation that we're going to look at or use today is called the compound interest formula. Which is FV equals PV times 1 plus R over N to the NT. So FV is the future value, PV is the present value, R is the interest rate written as a decimal, N is the number of compounds per year, and T is time in years. Okay. So let's look at a couple of examples. So I'm going to write out kind of a situation, then we'll ask some different questions about that particular situation. so in 1996, there were 2,573 computer viruses. During the next 7 years, the number of viruses grew by 92% each year. The first thing we're going to ask is to write exponential growth model, giving the number of viruses n after t years. So if I go back and I write down my exponential growth model, looked like this, right? Okay. So let's remember again what these different letters represent in this formula. What does y represent? Yeah, that final amount or future amount. Are we given that in the problem? No. In part A, it says, write the exponential growth model giving the number of viruses after t years. So that's going to be a future amount, right? It says to use n in that spot, so I'm going to replace y with n. What did A represent? The beginning amount. How many viruses did we have in the beginning? 2,573. So I'll replace A with 2,573. And then what was R? The rate of change written as a decimal. So what's the rate of change? It was 92%, which as a decimal would be 0.92. And then it says after t years, so t was time, so we're just going to put t in that spot. So there's my equation that I'm going to be using. So if I read this, it's after t years. So that's how it wants me to write my model. Okay. So now I might ask another question. So the next question I'm going to ask is about how many viruses were there in 2003? So to do this, I'm going to use my model from before. What I'm looking for is a future amount, right? So I'm going to be looking for n. What I need to be able to find n, though, is I have to plug in a value for t. So what value of t am I going to plug in? Why 7?
7
Mm-hmm.
years.
Not just because 7 years was listed in the problem. Yeah. So 2003 is 7 years in the future from 1996. If that date there instead of 2003 had been 2002, it would be 6, etc. So that's why I'm going to plug 7 in for t. Yes. Yeah, so the t is going to be a length of time, not a year.
Oh, yeah.
It'll be a length of time, like 3 years, 5 years, 6 months, some length of time. Yep. And so now we'll just go to our calculator and type this in. So I get 247,485 if I round to the nearest virus. Well, it says about, so we should round. And it's hard to have like half of a computer virus, so rounding to the nearest virus seems to make the most sense there. Are we all okay there? So the next question we're going to ask is to estimate when there were 125,000 computer viruses. So again, we're going to be using our model that we created to do this. And which part of this equation are we looking for? We're looking for time this time, right? Everybody agree with that? How did we know we were looking for time? It asks when in the question. When is a time question, right? Good. Okay. So what are we going to plug in for n then? 125,000, because that's our future amount, right? We're trying to figure how far in the future that's going to be. Everybody happy there? So now we're going to try to solve for t. Can we do this algebraically? Well, do we know how to get something out of an exponent if we have a variable in the exponent? No, not really, right? That's going to be one of the goals this chapter, is to develop the machinery able to do this algebraically. But we're not there yet. So what can we do instead? You could guess and check, sure. But what if I wanted the answer accurate to like 2 decimal places? That guess and check becomes pretty awful now, right? So what I'm going to do is I'm going to think about this as a system of 2 equations. So the first equation is our model, and the second equation is that amount that we're trying to get to. And I'm going to solve this system of equations graphically. So remember back to first semester when we solved systems of equations. How do we solve this? What is the system or the solution to a system of equations look like graphically? It's the intersection of those 2 curves, right? So I'm going to use my calculator then to graph these 2 curves and find the intersection. Okay, so if you have your calculator with you, I'd encourage you to take that out and follow along. If you don't, just pay attention now, but when you get home tonight, if you can't remember how to do this, cue up this part of the video so you can see the steps on the calculator again. So if I want to graph this, where do I put things? If I'm going to graph something, where do I need to go on my calculator? The y equals. Great. If I have anything in my y equals menu, I want to get rid of that. So let's clear anything out that we might have in there. In addition, we should check up here at the very top where it says plot 1, plot 2, plot 3. None of those should be highlighted. Notice on my screen, none of those are highlighted. If one of those is highlighted for you, use your arrows, move up to that spot, and press enter to unhighlight that spot. Okay? So in our case, when we write this, y is going to be the same thing as n, and x is going to be the same thing as t. So my first equation is going to be 2,573 times 1.92 to the x. So the y is already in our calculator, and then the x is going to be the same thing as my t. My next equation is just n equals 125,000. So we said n and y are the same thing, so the y is already there. So I just need to type 125,000. Everybody okay there? All right. Now, if I just hit graph right now, am I likely going to be able to see what's going on here? Probably not. Notice the numbers in this equation are very big. So we're going to have to pick a window here that makes some sense. So in our function here, x was the same thing as what variable? T, right? So t is representing time. So I know time can't be negative. That wouldn't make any sense. So what's a good smallest value of t? 0, right? That seems reasonable to me. And what's a good largest value of t? 7, because we know this model is good for 7 years, right? That's the way it was described in the problem. Great. Let's do 7 there. The y variable is representing n, which was our future value. What's a good minimum value for the future value here? Well, I wouldn't do 125,000 as the minimum. I would do 2,573. Because over that 7 years, that's the least amount of computer viruses we're going to have. Now, in the interest of just making it a little bit neater, I'm just going to do 2,500 or 2,500. But that's how I'm getting that number. Does that make sense to everyone? That's the least amount of computer viruses I would see was 2,573. No, I'm using a positive number there. Yeah. Okay. The Y max is the maximum amount of computer viruses. So let's go back and notice what we found in part B. This was the number of viruses after 7 years, right? That'd be the most amount of viruses we could encounter during our model. That makes a good candidate for the Y max. So I'm going to do 250,000 for the Y max, which is just a little bit more than what I got when I plugged 7 in for T. Everybody okay there? Okay. Does it make sense on how I chose those values for my X min and X max? Yes. Yeah, 25 with 4 zeros. So here's my graph. So the curve that's coming in right now is our model, and the straight line is for 125,000. So what I'm interested in is this point right here at their intersection. When you guys hit graph, is this what you got? Or all pretty much the same thing? Might look a little different depending on. Okay, so to find this point, what we're going to do is we're going to press second and then the trace command. These options here all are things that I will use on my graph. Which one of these sounds like what we need? Intersect, right? Because we're interested in the intersection of these two things. So let's scroll down and select the intersect command. So notice on my screen now, the calculator is going to ask me some questions. So the first question it asks is first curve. You notice you can see the cursor on my calculator here that's on the model. So as long as I pick anywhere on that line, I'm okay. So I'll just press enter. It's automatically toggled now to the next line. Anywhere on the straight line will be fine. That'll answer the question for my second curve. And then it asks for a guess. So I'm just going to use the left and right arrows to scroll over near where that intersection is, and then press enter again. And you'll notice at the bottom of the screen now, the calculator's given me an answer to my question. It says the intersection is at x equals 5.95 yada, 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 and y is 125,000. So what does this tell me now? That t, remember, was the same as which variable? X. So that value for x that I got would be my value for t. So I'll say about 5.95 years. Everybody okay with this idea? Let's do another, yes? Okay. So this next example, we have that a new snowmobile costs $4,200 and the value of the snowmobile decreases by 10% each year. We want to write an exponential model giving the value of the snowmobile in terms of y after t years. So I'll start by using my general exponential growth or decay model. And remind me again what y represents. That final or future amount, right? So the value of the snowmobile in the future would be that future amount. So it says to use y, so I don't have to change anything there. What does a represent? The beginning amount or current amount, right? So what is the current value of the snowmobile? Yeah, 4,200. And then what does R represent? The rate of change written as a decimal. What's the rate of change here? Close. Close. Read the words here a little bit. What? Negative 10%. Why is it negative? Yeah, because we have decreasing. So I'm going to write this as negative 0.1. Again, 10% is 0.1 as a decimal. So what kind of exponential model is this? If it's it's decay, right? So you got to make sure you're reading the words there. Notice on the previous one it said increased by 92%. So there we didn't have to think too much about it. But the words matter, not just the numbers. So you have to be a little bit careful there. And then it says it's after t years, so we'll just use t for t again. So there's my model. Everybody feel okay there? So it says, next I ask you to estimate the value of the snowmobile after 5 years. Okay, so we'll use our model that we just created in the previous one. How did I get the 0.9 there? Yeah, exactly. 1 plus the negative 0.1 gives me the 0.9, so I just simplified there a little bit. Which variable are we looking for, y or t? We're looking for y because it's the value of the snowmobile, right? So what am I going to have to plug in? A value for t. In this case, what would that value of t be? 5. So here it was a little bit nicer because they told you the length of time. They didn't give you dates, so you didn't have to find t. It was just what it was, right? Okay, so we'll go to our calculator, and we'll do 4,200 times 0.9 to the 5th. And we get 2,480. How should I round that number, I guess? I would round it like this. Why would I round it there? What is this quantity that we're getting? Money. So where should we round money to? The penny, right? Everybody feel okay there? As opposed to the previous problem where we were rounding number of computer viruses, that would round to a whole number. Money would round to the penny. So you have to use a little bit of common sense about what it is, that quantity that we're rounding to round appropriately. But that's hopefully not hard to see if you think about it for a minute about how you'd want to round that. Okay. The next question we'll have says, estimate when the value of the snowmobile is 1,500. So just like we did before, what we're going to do is we're going to use our model. Oops, I wanted red. And a system of equations to solve this. Everybody okay there? Okay. So we'll set this up just like we did before. We'll go to our calculator, and to the y equals menu, type in our first equation. Again, I'm using x instead of t because that's the variable my calculator has. So I'll do that. That's easy enough. Next thing I'm going to do is change my window. So again, the x is representing time. So 0 is usually a good minimum for time. In this case, do we have a good idea of what the x max should be? It's not really given to us in the problem, right? Well, we know it's going to be more than 5 because after 5 years, the value is more than 1,500 based on our previous answer, right? So maybe let's try like 10 is maybe a decent guess. If we have to, we can always make it bigger and go back in. Well, because it's a decay. So the longer the time goes, the less value we're going to have. Are you good with that?
Yeah.
Okay. So if it was growth, yes, you'd be right on, but we're not growing here, we're decaying. Yep. Okay. So my minimum value would be, what's a good minimum value here? Remember, we're decaying. How about 0? Right? The least value that snowmobile could ever have is 0, right? It can't be worth negative amount. You guys buy that? It might feel like it if it has to keep getting repaired or something, but... And what's a good maximum value then? $4,200, right? The initial cost of the snowmobile. That snowmobile is never going to be more valuable than the day you buy it, right? Everybody feels okay with how I picked the values there? Okay. So let's hit graph. So this curve is the curve for the value of the snowmobile. And there's my straight line is for 1,000. It looks like I have an intersection here. If it turns out not to work, if the calculator gives me some issues, I can always change my window and make that x a little bit bigger to where I can definitely get the intersection on there. But I think the intersection's there. So we'll press second and the trace button to open up that menu. We'll select the intersect command. For curve 1, we'll pick the value of the snowmobile curve. Curve 2, we'll pick the 1,000. And then we'll scroll over to where it looks like that intersection is and pick somewhere where it looks like the intersection as our guess. And there we go. It barely was on there, but it was good enough. It says that that intersection occurs at 9.77 years. What do you guys think there? Sounds okay? Okay. Let's do one more example, and then we're probably good for today in terms of examples. This one will be a compound interest example since we haven't used that model yet. So here it says you deposit $4,000 into an account that pays 2.92% interest compounded quarterly. And then we want to find the account value after 10 years. So I'm going to start by creating a compound interest model for this. So this is my compound interest model that I gave you guys earlier today. What does FV represent? Future value, which is what we'd be looking for in this problem, right? We want the account value after 10 years. PV is the present value, which would be what in this case? 4,000 is correct. That's how much money we initially put in. What does R represent? The interest rate as a decimal. So in this case, it would be 0.0292. And then what does N represent? The number of compounds per year. How many compounds are happening here? 4. How did you get 4? Because it says quarterly, right? If we compound something quarterly, that's 4 times. Okay? And then I'd have T. So in part A, what is our value for, we're looking for the future value. Are we given a value for T? Yes, right? So I know that T is going to equal 10. So to find my future value, I'm just going to plug in 10 for T and type that into my calculator. So I have 4,000 times 1 plus 0.0292 divided by 4 raised to the 4 times 10. So if I press enter, I have 5,350.73. It's a pretty good deal for sitting around not doing anything, right? Made $1,000 for doing nothing other than leaving your money with the bank. Okay. What if we ask how long would it take to double our investment? So what value are we looking for here? T, right? Because it's asking how long. That's another time question. Okay? So if I think back to our model that we had, we had this, right? We're looking for T. So what is our future value here going to be? 8,000. How did you get 8,000? It's double our investment. Exactly right. Good. So this is the equation that I'm going to try to solve. Notice we're in the same predicament that we were earlier, where we're not going to be able to do this algebraically. So we're going to use our calculator to do this. So go to the y equals menu, and I'll do 4,000 times 1 plus 0.0292 divided by 4 raised to the 4x. And then I'll have 8,000 here. For my window, x is representing time. So 0 is a good minimum. The maximum I know has to be more than 10 because 10 only gets me to 5,000. I don't really know what it's going to be. I'm just going to pick a big number like 50. If I have to, I can go back and make that bigger yet if I need to, but I'm just taking a guess. I know it has to be bigger than 10. That's all I know. And probably a lot bigger than 10, right? Because 10 only got me to 5,000. Okay? My minimum value, 4,000, is the amount we started with. We want to get to 8,000, so I want to be able to see 8,000. So I'm going to pick like 9 or 10,000 just so it'll be easy to see that line. Let's hit graph. So there's my function. And there's my 8,000. So I can see the intersection. Happened way before 50 years. That's good. Select the intersect command. Enter guess. And I get about 23.82 years. Everybody okay there? So still basically the same thing, right? We're just using a different model to do our work with. But the process really didn't change any, right? Do we feel okay? All right, we'll stop here.